The force due to gravity by a mass at the origin of the plane R2, the xy plane, is given by f of xy, vector valued function, equals some constant k divided by x squared plus y squared to the 3/2 power times the vector negative x, negative y. K is a positive constant that depends on the masses of the objects involved, and we would like to find the work done by this force on an object as that object moves in a straight line from one point to another. So first let's discuss this function. You may be familiar with the force of gravity between two objects is Newton's gravitational constant times m1 times m2 divided by r squared. And they actually agree. This formula and this formula, they actually agree. This one is giving you the magnitude of the force with the understanding that the direction is from the perspective of one object. It is in the direction towards that object. So in our case, our object, the main object is at the origin that's exerting the force. And then we have another object at some point xy, and the force will be towards the origin, that is in the direction of the vector negative x, negative y, which we can see right there. So that vector is accounting for the direction of the force. Now, what about the magnitude of the force? The magnitude of the force, according to this formula, would be the constant k over x squared plus y squared to the 3/2 times the magnitude of this vector negative x, negative y, and the magnitude of this vector is the square root. So we get k times the square root of negative x squared plus negative y squared, you can drop the negatives, divided by x squared plus y squared to the 3/2. Now the square root is the 1/2 power, so that cancels with the 3/2 power, just leaving the power 1 on the bottom. And x squared plus y squared is r squared, so we get a constant that depends on the masses and Newton's gravitational constant divided by r squared. So the magnitude is indeed the same here and here. Okay, so now our object is going to be moving. We have the main object is at the origin, and we have an object moving from the point -1, 0 to the point -1, 1. So the object is moving in this direction. And we want to find the work done, by our force, the gravitational force, as the object moves. And it seems the object is moving away from the origin, the mass at the origin, and so work will be done against gravity, and so therefore the work should be a negative quantity. Now, let's compute it. To compute work done by a force, the work, we integrate the force dotted with dr, where dr is related to the direction vector of the curve that the object is moving along. So we have to compute this line integral. And the definition of this line integral, if the curve is given by r of t equals x of t comma y of t, then where t goes between two values, we have a starting point and an ending point for our section of a curve, really, then the work done as we move along a section of a curve will be the integral from a to b of the vector function describing the force dotted with the tangent vector dt. So the tangent vector would be x prime of t, y prime of t. And here x and y would be expressed in terms of t. If the object is moving along this curve, then x is x of t and y is y of t, where the curve is described by x of t, y of t. So we'll have an integrand here purely in the variable t. So in our particular situation, if an object moves from a point P to a point Q, then that means that we can parameterize that line segment as the vector for P plus t times, that's the position vector for P, plus t times the vector from P to Q, where t goes between 0 and 1. So in our case, the position vector of the point -1, 0 is the vector -1, 0, plus t times the vector from P to Q. So we take the coordinates of Q and subtract the coordinates of P. -1 minus -1 is 0. 1 minus 0 is 1. So we get -1, 0 plus t times 0, 1. And putting it together, the x component is the constant -1, and the y component is t. So this is r of t. So x of t, y of t, and t goes between 0 and 1. So r prime of t is 0, 1. Derivative with respect to t is 0. Derivative is 1. So now, getting back to our work calculation, it's going to be the integral from 0 to 1. T goes from 0 to 1. Our function f, where for x, we're going to be putting in -1, and for y, we're going to be putting in t. So for x, we put in -1. That just makes a 1, and this makes a t. So we have k over 1 plus t squared, 1 squared, which is 1, to the 3/2 times the vector. We're putting in -1 for x, so this becomes 1, and we're putting in t for y, so this becomes -t. So 1 comma -t, dotted with r prime of t, which is 0, 1, dt. So this is, we can put the k in the front, integral 0 to 1. This dot product is 1 times 0, 0, plus -t times 1, so -t. So we get -t over 1 plus t squared to the 3/2 dt. And we'll put our negative sign in the front. To integrate now, we do a u substitution. U equals 1 plus t squared. Du is 2t dt. So I'll put a 2 here and divide by 2 there. And as t goes from 0 to 1, if t is 0, that means that u is 1 plus 0. So u is going to go from 1 to, if t is 1, then u is 1 plus 1, which is 2. So u is going to go from 1 to 2. And so our integral is negative k over 2, integral from 1 to 2 of, now we have 2t dt, that's du, and we have u to the 3/2, that's u to the negative 3/2. So we have a basic integral now, and this will give us our answer. The antiderivative, we have negative k over 2, antiderivative of u to the negative 3/2, we have to add 1 to the power, that makes -1/2, and divide by -1/2, that multiplies by -2, from 1 to 2. And the -2 cancels with the -1/2, and this is 1 over the square root, and so we get k times 1 over the square root of 2 minus 1. So there is the work done against gravity, because this is a negative number. 1 over the square root of 2 is less than 1, and k was a positive constant. So work was done against gravity, which is what we expect, because our object was moving away from the massive object at the origin whose gravitational pull we were escaping. So work is done against gravity at negative value.